30 September 1999, 10:35 a.m., JCO Conversion Test Building, Tokai-mura, Ibaraki Prefecture, Japan. In a concrete room sized for chemical work, 3 technicians stand near a 45-centimeter precipitation tank. Routine monitors click at background. The 7th stainless steel bucket of uranyl nitrate, 18.8% uranium-235, pours through a funnel. Operators expect another batch completed by noon. Instead, a blue-white flash. Gamma alarms sound simultaneously. The tank now holds approximately 16 kilograms of uranium, nearly 7 times the regulatory limit per batch. Within seconds, whole-body doses measured in double-digit sieverts begin accumulating in 3 men standing closest to the vessel. Outside, perimeter monitors register values that match no expected scenario. For the next 19 hours, an unshielded tank will behave like an unlicensed reactor, while Japan confronts a word regulators had judged not credible at this facility: criticality. In the early 1990s, a licensing file sat on a desk at Japan's Science and Technology Agency in Tokyo. The document described the JCO uranium fuel conversion test facility in Tokai-mura, Ibaraki Prefecture, approximately 135 kilometers northeast of Tokyo, as a small throughput operation producing uranyl nitrate solutions for power reactors and occasional batches for the Joyo experimental fast reactor. The design basis noted enrichment up to 20% uranium-235, with criticality control ensured by equipment geometry rather than by active systems. Regulators expected a low-risk chemical plant feeding the fuel cycle, not a site where criticality was plausible. The conversion test building was excluded from Japan's national plan for the prevention of nuclear disasters. No criticality alarm system was installed because criticality was judged not credible by safety analysts who reviewed the approved flow sheet. JCO Komiken, later a subsidiary of Sumitomo Metal Mining, operated the facility under oversight from the Science and Technology Agency and the Nuclear Safety Commission. The Power Reactor and Nuclear Fuel Development Corporation served as client for Joyo fuel batches, requiring medium enrichment. The approved process appeared straightforward on paper. Uranium dioxide or uranium trioxide powder was dissolved in a dissolution tank, then transferred to a tall, narrow buffer column for homogenization and metering, then moved to the precipitation tank with a surrounding cooling water jacket. Criticality safety depended on geometry. The column's slender shape and a 2.4 kilogram uranium batch limit to the tank were the core engineered protections. No active interlocks, no criticality detectors, no emergency boron injection, just passive dimensional control and procedural discipline. The International Atomic Energy Agency Lessons Learned report would later note that the IAEA licensed process incorporated sufficient margins against criticality, provided that the approved procedures were followed. That final clause carried the entire weight of the safety case. By relying on geometry and procedure rather than active safeguards, the system assumed that operators would never bypass the column and never exceed mass limits in the tank. The design left no margin for human shortcuts or production pressures. On paper, the conversion test building could not produce a criticality. In practice, a single tank in that building would eventually behave like a low-power reactor for 19 hours. Between 1993 and 1998, an internal operating manual circulated among workers at the JCO conversion test building in Tokai-mura. The 1996 edition described a simplified method: dissolving uranium powder directly in open buckets, bypassing the dissolution tank and buffer column entirely. The text never appeared in documentation approved by the Science and Technology Agency. The expected regulatory process required that any change to equipment, sequence, or geometry undergo STA review and safety analysis before implementation. The actual practice diverged sharply. From about 1993, JCO operators adopted a bucket method for redissolution and transfer. A 1995 JCO Safety Committee meeting endorsed the practice, and the unofficial 1996 manual institutionalized it without notifying STA. Production managers chaired the Internal Safety Committee. STA inspectors conducted periodic audits, but these focused on paperwork compliance and did not detect the bucket method in use on the shop floor. The shortcut sequence worked as follows. Uranium powder and nitric acid were combined in 10-liter stainless steel buckets. The resulting uranyl nitrate solution was then ladled with 5-litre buckets and poured via funnel directly into the precipitation tank. The licensed buffer column, the geometric control on which the entire criticality safety case rested, was removed from the process flow. Quantifying the risk reveals how quickly limits could be breached. At concentrations of approximately 380 grams uranium per litre, a 5-litre bucket carried up to roughly 1.9 kilograms of uranium. 7 buckets could exceed the licensed per batch mass in a few minutes, with no engineered barrier to prevent it. The Nuclear Safety Commission and STA final report stated that hazardous practices using buckets had been permitted since 1993, and that a 1996 manual recommending bucket use was never submitted for regulatory approval. Cost and schedule pressures, combined with limited regulatory attention to a small facility, allowed an unreviewed operating mode that removed the geometric criticality control the license depended on. By the late 1990s, the only place the tall buffer column still controlled mass. To the precipitation tank was in the drawings attached to the original license. The equipment sat unused. The approved flow sheet existed only on paper. The gap between documented procedure and shop floor reality had widened to the point where the facility's actual criticality margin was unknown to everyone outside the conversion building, and perhaps to many inside it as well. On the morning of 30 September 1999, a work order authorized production of 18.8% enriched uranyl nitrate for the Joyo experimental fast reactor, the first such batch since 1996. Uranium oxide powder, nitric acid, and stainless steel buckets were staged near the precipitation tank in the conversion test building. For rare, higher-risk work involving medium enrichment, the expectation would be refresher training, requalification, and strict adherence to the licensed flow sheet. The reality was different. The 3 assigned workers, Hisashi Uchi, 35 years old, Masato Shinohara, approximately 39 to 40, and Yutaka Yokokawa, 54, received no special retraining on medium-enriched solutions and followed the informal bucket procedure they knew from years of routine work. Reconstructions by the Nuclear Regulatory Commission and IAEA placed the men in specific positions, Uchi leaning over the tank, Shinohara standing on a platform beside it, Yokokawa seated at a desk approximately 4 meters away. The physics of critical mass governed what would happen next. For a solution of 18.8% uranium-235, geometry and moderation dominate the safety margin. A shallow, wider tank with a water reflector is far less forgiving than a tall, slender column. Water serves a dual role, as coolant in the jacket surrounding the tank, and as both neutron moderator within the solution and reflector outside the vessel. The bucket loading method closed the loop, delivering fissile material directly into the least favorable geometry. Operations on the day of the accident were, as one technical summary noted, to produce uranyl nitrate solution with an enrichment of 18.8% for Joyo. By mid-morning, approximately 40 litres containing roughly 16 kilograms of uranium had accumulated in the vessel, nearly 7 times the licensed batch limit. Restarting Joyo fuel production with medium-enriched material, but with practices developed for lower-risk work and no recent experience with this enrichment level, placed a large criticality hazard directly into an unshielded, non-engineered geometry. The men in the room had operated the facility for years. They knew the bucket method. They did not know that the combination of enrichment, mass, and geometry had placed them on the edge of a threshold that no small fuel facility in Japan had ever crossed. By 10:30 a.m., more fissile material was already in one unshielded tank than any approved procedure had ever permitted to be there. An area gamma monitor near the precipitation tank showed routine readings as the 6th bucket went in. The needle traced a steady line near background, the kind of trace operators had seen thousands of times. As the 7th bucket of uranyl nitrate was poured through the funnel, witnesses later described a blue-white flash and near-simultaneous alarm tones from the gamma monitor. Operators expected a passive chemical vessel at atmospheric pressure, with no sudden power changes. What occurred was crossing critical mass in a water-moderated, water-reflected configuration. The system achieved prompt criticality, triggering a rapid power spike in milliseconds as the neutron population grew exponentially without waiting for delayed neutron emission. Hisashi Uchi was bent over the tank, his upper body directly above the solution. Masato Shinohara stood on the platform, slightly farther from the center of the vessel. Yutaka Yokokawa sat at the desk, approximately 4 meters from the tank's edge. All three reported the flash and immediate physical symptoms: nausea, a metallic taste, disorientation. The Department of Energy and Nuclear Regulatory Commission descriptions reconstructed the configuration. Approximately 40 liters of uranyl nitrate solution containing roughly 16 kilograms of uranium, enriched to 18.8% uranium-235, in a 45 centimeter diameter stainless steel tank with a water-filled cooling jacket surrounding the vessel. The solution itself was moderated by the water content of the nitrate. The jacket provided additional neutron reflection, bouncing neutrons back into the solution to sustain the chain reaction. Initial dose estimates, derived from biodosimetry and clinical symptoms, placed whole-body exposures at approximately 17 sieverts for Uchi, 10 sieverts for Shinohara, and 3 sieverts for Yokokawa, all in mixed neutron-gamma radiation fields. To provide context, annual occupational limits in most countries are 50 millisieverts. A dose of 4 to 6 sieverts is generally considered lethal without intensive medical intervention. The Physics Today and NRC summaries noted that all 3 workers immediately reported seeing blue-white flashes and soon developed nausea and vomiting, classic prodromal symptoms of severe acute radiation exposure. Hand-loading the tank in large, discrete increments allowed the final bucket to push the system from subcritical to prompt critical in a single step, precisely as workers were closest to the source. The geometry they had bypassed, the tall buffer column, would have metered the uranium in slowly, preventing any single addition from crossing the threshold. Within seconds, the doses being deposited in that room were no longer measured in millisieverts per year, but in sieverts per second for the men nearest the tank. A JCO control room telephone log recorded a call to company headquarters at approximately 10:40 a.m., reporting a radiation exposure accident at the conversion test building. No one yet used the term criticality accident. The framing reflected an expectation. Radiation incidents at fuel facilities were understood as leaks, spills, or contamination events, problems of containment, not of nuclear physics. Expected response protocols focused on short-lived excursions or localized contamination that could be addressed by evacuation, sealing, and decontamination. The actual situation was fundamentally different. The precipitation tank remained at or near critical. Neutron and gamma emission continued while staff debated event classification and next steps. JCO plant emergency coordinators contacted the company president. Tokai village officials and Ibaraki prefecture authorities began receiving fragmented reports. Officers at the Science and Technology Agency's Emergency Center started assembling information, but early communications provided limited technical detail about the ongoing source term. The 3 severely exposed workers were evacuated from the building within minutes of the flash. They were transported to the National Institute of Radiological Sciences in Chiba for medical evaluation and treatment. Other JCO staff performed initial radiation surveys near the conversion test building perimeter, using portable instruments to assess dose rates and contamination levels. Without a criticality alarm system and with limited real-time neutron dosimetry, survey teams could not easily distinguish an ongoing chain reaction from a static radiation source. The gamma monitors showed elevated readings, but gamma radiation alone does not confirm fission. Neutron detection requires specialized instruments, and few were immediately available on site. The IAEA report noted that early communications described the event as a radiation exposure accident, with the continuing criticality not recognized for some time. The misclassification had consequences. Framing the event as a leak or exposure rather than as an active reactor delayed actions specifically focused on stopping fission, such as removing the neutron reflector, and complicated protective action decisions for the surrounding population. For more than an hour, the only operating reactor in Tokai-mura was one that appeared on no official reactor list, had no control rods, no scram system, no containment, and no radiation shielding beyond the concrete walls of a chemical process room. The solution in the tank fluctuated around criticality, with power rising and falling as thermal expansion, gas bubbles and convection currents changed the geometry and moderation. Each pulse added dose to anyone nearby and released additional fission products into the vessel. The monitors at the building perimeter continued to read values that made no sense for a static source. The tank was not leaking, it was operating. A Japan Atomic Energy Research Institute neutron monitor, located several kilometers from the JCO facility, recorded a sharp spike in count rate near 10:35 a.m. on 30 September. The trace showed an abrupt rise, then an irregular but sustained elevation over the following hours. Jerry analysts marked the anomaly and began correlating the distant detector signal with reports arriving from the JCO site. Any inadvertent criticality excursion would be expected to self-terminate quickly. Thermal expansion of the solution, gas generation from radiolysis, and negative reactivity feedbacks should quench the chain reaction within seconds or minutes. The actual behavior observed at Tokaimura was different. Detailed reconstruction by researchers showed an initial burst phase lasting approximately 25 minutes, characterized by variable power and multiple subcritical oscillations, followed by a plateau phase in which the tank remained at or near critical for about 19 hours. The JERI environmental monitoring team continued recording data. JCO safety staff performed repeated dose rate surveys near the conversion test building boundary, documenting the persistence of elevated radiation fields long after the initial event. Time series data from monitors positioned approximately 60 to 70 meters from the tank showed neutron dose equivalent rates of roughly 4 to 4.5 millisieverts per hour and gamma dose rates of approximately 0.5 millisieverts per hour, measured about 11 hours after the onset of criticality. These values were roughly 1,000 times typical background levels of about 0.5 microsieverts per hour. Integrating the fission power over the 19-hour plateau period, using fission product radiochemistry and neutron transport calculations, researchers later estimated a total of approximately 2.5 times 10 to the 18th fissions in the tank. To provide a benchmark for scale, the dose rate of 4 millisieverts per hour at the site boundary, sustained over several hours, would deliver a whole-body dose on the order of tens of millisieverts, equivalent to roughly several hundred chest X-rays, assuming approximately 0.1 millisieverts per standard chest radiograph. A technical paper summarizing the accident stated, "The total number of fissions during the accident was evaluated to be about 2.5 times 10 to the 18th. For comparison, a small research reactor operating at 1 kilowatt thermal power for 1 day produces roughly 10 to the 18th fissions." The long plateau phase meant that radiation dose accumulated to workers, emergency responders, and nearby residents as a function, not just of distance, but of how long the tank was allowed to remain critical. Every hour of delay added exposure. Every decision about approach, shielding, and evacuation had to account for a source that was not diminishing. By dawn on 1 October, a process tank designed for chemistry had quietly produced a fission total comparable to weeks of operation in some research reactors. In the Tokai village municipal office, staff spread a large-scale map on a conference table. Using a compass and ruler, they drew circles centered on the JCO conversion building, 350 meters, 10 kilometers. Faxed radiation survey readings and notifications from the Science and Technology Agency arrived as officials debated who must evacuate immediately and who must remain indoors. Expected emergency planning had focused on Japan's large power reactors. The conversion test building was not included in national nuclear disaster scenarios. Protective action guides, dose projection models, and evacuation routes had been developed for reactor accidents involving core damage and large radioactive releases. A criticality accident at a small fuel facility, with neutron and gamma emissions from an unshielded tank, presented a different challenge. Real-time decisions had to be made for a facility that had never been drilled, using dose monitors and projection tools calibrated mainly for reactor-type accidents. The Tokai Village Mayor's Office, Ibaraki Prefecture Disaster Management staff, and STA representatives coordinated response actions by telephone and fax as information arrived in fragments throughout the day. Around 3 p.m. on 30 September, authorities ordered the evacuation of 161 people from 39 households, within 350 meters of the accident building. Residents were told to gather essential belongings and report to a designated assembly point. Many did not understand the nature of the emergency. Some asked whether a fire or chemical spill had occurred. As neutron monitor readings remained elevated into the evening and uncertainty about the source term persisted, the protective action radius expanded. Around 10:30 to 11:30 p.m., approximately 310,000 residents within 10 kilometers of the JCO site were instructed to remain indoors and suspend outdoor activities, including agricultural work. Windows were to be closed, ventilation systems turned off. Well water use was discouraged pending sampling results. Over the following 10 days, about 10,000 people underwent medical examinations and radiation screening. Later dose reconstruction identified 667 people, workers, emergency response personnel and residents, with measurable radiation doses above normal background levels. Most individual doses were in the low millisievert range, well below thresholds for deterministic health effects, but the numbers documented the breadth of the affected population. Dose estimates were eventually produced for 234 residents, 169 JCO employees, and 260 emergency workers. The diversity of these groups reflected the scale of the evacuation and emergency response, involving local fire departments, police, medical teams, and health physics, specialists from multiple organizations. For residents within 10 kilometers, a plant they had scarcely noticed before that morning suddenly dictated whether they could step outside their front doors, whether their children could go to school, whether vegetables in the garden could be eaten. The invisible boundary drawn by neutron flux and gamma dose rate became the most tangible fact in their lives for the next several days. At the National Institute of Radiological Sciences in Chiba, cytogeneticists examined blood samples drawn from the 3 JCO workers within hours of their arrival. Chromosome aberration analysis, specifically counting dicentric chromosomes and ring forms in cultured lymphocytes, provided a biological dosimeter independent of physical reconstruction. The patterns indicated whole-body doses in the double-digit sievert range for 2 of the men. Expected occupational exposures in the nuclear industry are measured in millisieverts per year, with regulatory annual limits around 50 millisieverts for workers in most countries. Occasional incidents might result in exposures of a few tens of millisieverts, rarely exceeding 100 millisieverts. Estimated doses of approximately 17 sieverts, 10 sieverts, and 3 sieverts for Ouchi, Shinohara, and Yokokawa respectively represented levels associated with catastrophic bone marrow failure and multi-organ injury, doses rarely seen in civilian nuclear industry history and almost never survived. Clinicians at NIRS and the University of Tokyo Hospital initiated aggressive treatment protocols. Dose reconstruction proceeded in parallel using multiple methods: lymphocyte depletion curves tracked over the first days, chromosome aberration frequencies, clinical prodromal symptoms, and later activation analysis of sodium-24 in blood samples. All methods converged on estimates placing 2 of the workers beyond conventional survivability thresholds. Treatment included peripheral blood stem cell transplantation, intensive supportive care with broad-spectrum antibiotics and antifungals, blood product transfusions, growth factor administration, and strict barrier nursing to prevent infection in patients with destroyed immune systems. Ouchi and Shinohara were placed in isolation rooms with positive pressure filtered air. Medical staff wore full protective equipment for every interaction. The medical case unfolded over months. Hisashi Ouchi survived 83 days, dying on 21 December 1999 from multiple organ failure after a prolonged battle marked by brief periods of apparent stabilization followed by cascading complications. Masato Shinohara survived approximately 7 months, dying in April 2000. Yutaka Yokokawa, with an estimated dose of 3 sieverts, severe but below the acute lethal range, was discharged from hospital in December 1999 with chronic radiation injury but stable condition. Medical literature, summarizing the Tokaimura cases, reported that these doses rank among the highest ever reported for survivors of accidental irradiation in a peaceful nuclear facility. The intensive care provided, including experimental stem cell therapies, represented the limit of medical science's ability to intervene in acute radiation syndrome at such extreme dose levels. Workers' positions at the moment of criticality, distances measured in centimeters and meters from the tank surface, and the duration of exposure before evacuation determined orders of magnitude differences in absorbed dose and ultimately in survival. Ouchi, leaning over the tank, absorbed a neutron and gamma field at nearly point-blank range. Shinohara, standing slightly farther away, received roughly half the dose. Yokokawa, at his desk 4 meters distant, received less than 1/5 the dose of his colleague at the tank. Beyond the evacuation statistics, the dose maps, and the fission totals, the accident's most severe consequences were concentrated in 3 human bodies that had been within meters of the tank when the 7th bucket tipped the balance. Around a conference table at the Japan Atomic Energy Research Institute on the night of 30 September, nuclear safety experts sketched the JCO precipitation tank and its cooling water jacket. The working hypothesis emerged from the physics. The water surrounding the vessel was acting as a neutron reflector, returning neutrons to the solution that would otherwise escape, thereby sustaining criticality. Simply evacuating the building ended direct human exposure, but as long as the reflector remained, the tank continued to emit neutrons and gamma rays. Monitors positioned at the building perimeter and at distances of hundreds of meters showed dose rates remaining elevated hours after the process room was emptied. The solution in the tank had reached a quasi-equilibrium. Thermal expansion and gas bubbles periodically reduced reactivity, allowing power to drop. Then contraction and bubble collapse allowed power to rise again. The oscillations were irregular but persistent. JERI analysts briefed JCO operations staff and Science and Technology Agency officials on a proposed intervention. Drain the water jacket to remove the reflector, breaking the neutron economy and forcing the system subcritical. The plan carried risk. Workers would need to approach the building, locate the jacket drain valves, and manually open them, all while the tank remained an active, unshielded radiation source. An emergency dose limit of 100 millisieverts per worker was established for the high-dose tasks, 20 times higher than Japan's normal annual occupational limit, but judged acceptable for averting a continuing radiological emergency. Around 2:30 a.m. on 1 October, controlled operations began. Teams of workers in protective equipment approached the conversion building in rotation, working in short intervals to minimize individual exposure. Valve handles were turned. Water began draining from the jacket into a collection sump. As the water level dropped around the tank, neutron monitors at the perimeter began showing declining count rates. By approximately 6:15 a.m., neutron monitors had returned to background levels, indicating the end of the chain reaction. At 8:30 a.m., to provide an additional shutdown margin and prevent recriticality if conditions changed, workers added a boric acid solution to the uranyl nitrate in the tank. Boron-10 is a strong neutron absorber. Even a small concentration ensures subcriticality regardless of geometry or moderation. The IAEA report concluded that the chain reaction was terminated following the removal of the cooling water surrounding the precipitation tank. Recognizing the reflector effect and acting on it with a specific engineering intervention, draining the jacket was the decisive moment that ended the accident. Until that action was taken, the criticality was self-sustaining and would have continued indefinitely. After 19 hours, the same water that had been installed for cooling and safety, a routine feature of chemical process equipment, proved to be both the factor sustaining the chain reaction and the key to stopping it. The accident illustrated a principle of nuclear criticality safety. Every material and every design feature must be evaluated for its effect on neutron balance. Water cools, but water also moderates and reflects. In the wrong geometry, a safety system becomes a hazard. The final log entry was brief. Criticality terminated at 06:15, 1 October 1999. In a radiation counting laboratory in late 1999, gamma-ray detectors measured spectra from environmental samples and from gold jewelry loaned by local residents. The gold rings, coins, and watch components served as passive neutron dosimeters. Neutrons from the criticality had activated gold-197 nuclei, converting them to gold-198 through neutron capture. Gold-198 decays with a half-life of approximately 2.7 days, emitting beta particles and characteristic gamma rays at 412 kilo-electron-volts. Rough public dose estimates could be inferred from a few fixed radiation monitors and conservative atmospheric dispersion models. Detailed activation analysis and fission product radiochemistry provided a high-resolution picture of neutron and gamma fields around the site, allowing dose reconstruction for individuals based on their location during the 19-hour criticality. Researchers, including members of JERI working groups, collaborated with university laboratories to analyze the activation data. By measuring the specific activity of gold-198 in becquerels per gram of gold, scientists back-calculated the neutron fluence, neutrons per square centimeter, that each sample had received. Neutron fluence combined with energy spectrum information and conversion coefficients yielded effective dose estimates in sieverts. The dose distribution showed maximum effective doses of approximately 21 millisieverts for the most exposed residents, 48 millisieverts for the most exposed JCO employees not in the immediate accident room, and 9.4 millisieverts for the most exposed emergency workers. The majority of individuals in all three categories received doses well below these maxima. Most resident doses were in the single-digit millisievert range or lower. Environmental monitoring confirmed low-level contamination in some vegetation samples near the facility, primarily from deposition of short-lived fission products, such as iodine isotopes. No contamination was detected in dairy products, drinking water supplies, or marine samples collected from coastal waters near Tokai-mura. The accident was primarily a direct irradiation event rather than a widespread contamination event. A comprehensive dose assessment published in the peer-reviewed literature concluded that no deterministic effects have been observed except for the three workers, who were in the process room at the moment of criticality. The finding underscored the critical distinction between on-site acute exposures at close range and off-site chronic exposures at distance. While 667 people received measurable doses above background, only the three workers in the immediate vicinity of the tank received doses high enough to cause tissue damage and clinical illness. Forensic dosimetry using activation analysis narrowed the uncertainty about public health impact, informing long-term health surveillance plans and legal compensation schemes. The precision of the gold activation method, able to detect neutron exposures corresponding to doses of a few millisieverts or less, provided objective data that helped resolve disputes about individual exposures and risk. Years after the accident, some of the most precise evidence about the event's geographic reach and intensity came not from engineered radiation detection systems, but from trace radioactivity in ordinary jewelry and pocket change, the gold in a wedding band, the coins in a resident's drawer, the metal clasp of a watch. All had recorded the neutron field with passive, incorruptible fidelity. In the Tokyo District Court during 2000 and 2001, prosecutors presented evidence in the criminal case against JCO Kobayashi and 6 of its employees. The indictment charged professional negligence resulting in death and injury, based on documented violations of nuclear safety regulations stretching back years before the accident. Expected practice in the nuclear industry required operators to maintain configuration control and notify regulators of any process changes that could affect safety. Reality at JCO had diverged sharply. Evidence presented in court showed that the company had introduced major process changes beginning in 1993, endorsed them through internal safety committee decisions in 1995, and codified them in an unauthorized operating manual in 1996, all without Science and Technology Agency approval. Prosecutors read from the 1996 internal manual, which explicitly recommended bucket use for dissolving and transferring enriched uranyl nitrate. They juxtaposed these pages with the STA-approved license documentation, which described the dissolution tank and buffer column process and never mentioned buckets. The gap between authorized procedure and actual practice was documented in the company's own records. 6 JCO employees, including the production department chief and supervising staff, entered guilty pleas to charges of negligence resulting in death and injury. The company president admitted corporate responsibility for the accident. Legal findings detailed the causal chain, management decisions driven by cost reduction and schedule pressure, inadequate training and qualification of workers for medium enriched fuel handling, failure to perform criticality safety analysis for the bucket method, and absence of oversight sufficient to detect the unauthorized practices. The Nuclear Safety Commission and Science and Technology Agency issued comprehensive final reports documenting root causes and recommending regulatory reforms. The International Atomic Energy Agency published a detailed lessons learned analysis for the international nuclear community. The accident was rated Level 4 on the International Nuclear and Radiological Event Scale, accident with local consequences, reflecting limited off-site radiological impact but severe on-site injuries and fatalities. For comparison, Level 5 denotes accident with wider consequences, Level 6 serious accident, and Level 7 major accident, such as Chernobyl or Fukushima. JCO's nuclear fuel processing license was formally revoked. The company exited the uranium conversion business, ending decades of operation at Tokai-mura. The conversion test building was eventually decommissioned and dismantled. Regulatory reforms followed. Japan enacted a new special law for nuclear disaster countermeasures, expanding emergency planning requirements to include all nuclear fuel cycle facilities, not just power reactors. Criticality alarm systems became mandatory at facilities handling fissile material above threshold quantities. Inspection frequencies increased, and training requirements were strengthened with specific provisions for infrequent or non-routine operations involving higher enrichments. International guidance on criticality safety, promulgated through IAEA safety standards and incorporated into national regulations worldwide, emphasized the lessons of Tokai-mura. Design, procedures, training, and oversight must form an integrated safety system. Failure in any single element can invalidate the others. Passive, safety features such as geometry control are effective only if administrative controls prevent their bypass. A facility once considered too small to warrant inclusion in national disaster plans became the case study that rewrote those plans. The regulatory architecture of Japan's nuclear sector carried the imprint of 2 deaths and 19 hours of uncontrolled fission in a stainless steel tank. A prefectural environmental monitoring report issued in the months following the accident summarized radiation surveys and sampling results from Tokai-mura and surrounding areas of Ibaraki Prefecture. The report presented tables of gamma dose rate measurements and analytical results for tap water, well water, rainwater, soil, vegetation, seawater, dairy products, and marine food products. Most entries recorded values near natural background levels or below detection limits. Expected public fear, shaped by media coverage of prior nuclear accidents, might have anticipated large contaminated zones, long-term agricultural bans, and evacuations lasting months or years. The measured environmental reality at Tokaimura was more modest. The accident was primarily an irradiation event, direct exposure to neutron and gamma radiation from the tank, rather than a large-scale environmental contamination event involving atmospheric dispersion of radioactive material. Environmental surveys identified low-level contamination in some vegetation samples collected within a few hundred meters of the JCO facility, consistent with deposition of short-lived fission products released from the tank during the 19-hour criticality. Iodine-131 and other volatile species were detected at trace levels. No significant contamination was found in drinking water supplies, dairy products, or seafood. Agricultural restrictions were brief and geographically limited. Ibaraki Prefecture Health and Environment Departments coordinated the monitoring effort with support from the Science and Technology Agency and independent review by citizens groups, including the Citizens Nuclear Information Center. The multi-party involvement helped build public confidence in the data. Consolidated dose figures from forensic reconstruction showed maxima of 21 millisieverts for residents, 48 millisieverts for JCO employees outside the accident room, and 9.4 millisieverts for emergency workers. The vast majority of individuals in all categories received doses well below these values. No off-site deterministic health effects, tissue damage, or acute illness caused by radiation were identified. The doses received by the public fell within the range where only statistical increases in long-term cancer risk are predicted, and such increases are difficult to detect epidemiologically above natural variation. Cleanup operations at the JCO site included installation of temporary shielding, such as sandbags and concrete blocks around the conversion test building. surface, decontamination of floors and equipment using chemical wipes and strippable coatings, controlled access with dosimetry monitoring, and eventual dismantling or decommissioning of contaminated process systems. Workers involved in cleanup received doses within occupational limits, managed through time and distance controls. Compensation settlements addressed economic losses and health concerns for affected residents. By mid-2000, JCO had reportedly agreed to pay settlements in thousands of individual claims, with total compensation estimated in the range of tens of millions of US dollars equivalent. Claims covered lost income for evacuees and businesses, medical examination costs, and psychological distress. A technical assessment noted that the contribution of atmospheric plume to off-site dose was negligible compared to direct irradiation from the unshielded tank. Most of the public dose was received by individuals who were outdoors and within a few hundred meters of the building during the 19-hour criticality. Distance and shielding by buildings reduced dose dramatically for the broader population within the 10-kilometer shelter zone. On monitoring graphs, radiation levels returned to baseline within weeks to months. Public trust in the safety culture of Japan's nuclear facilities, and specifically in small fuel cycle plants, without strong traditions of reactor-style rigor, took much longer to recover. In training courses for new nuclear workers during the 2000s, instructors displayed a slide showing 3 images. On the left, a schematic diagram of the JCO precipitation tank with dimensions and the surrounding water jacket. In the center, a photograph of 10-liter and 5-liter stainless steel buckets, ordinary industrial equipment that had defeated an engineered safety system. On the right, a photograph of a criticality alarm control panel, now mandatory in facilities handling significant quantities of fissile material. Earlier understanding held that serious criticality accidents belong to the history of early weapons programs, Los Alamos in the 1940s, Oak Ridge and Hanford in the 1950s, and to large reprocessing plants handling kilogram quantities of plutonium. The revised understanding after Tokai-mura recognized that a small conversion plant, operating with relatively modest enrichments and batch sizes, could produce a lethal criticality if geometry-based safety assumptions were quietly bypassed through unauthorized procedure changes. Japanese regulatory bodies responded by implementing sweeping reforms. A new special law for nuclear disaster countermeasures required all nuclear fuel cycle facilities, including small conversion plants, fabrication shops, and storage facilities, to be included in national and prefectural emergency plans. Quarterly inspections of fuel facilities increased in frequency and technical depth. Training requirements were strengthened with mandatory refresher courses for non-routine operations. Quality assurance programs were audited more rigorously, with specific attention to the alignment between approved procedures and shop floor practice. Internationally, the IAEA incorporated Tokaimura lessons into updated criticality safety guidance and training materials. Fuel cycle facilities in the United States, Europe, and other countries revisited their criticality safety evaluations, especially where manual material transfers and solution handling were part of the process. The accident demonstrated that criticality risk extends beyond reactor cores and reprocessing canyons to any operation that concentrates fissile material in geometries not bounded by rigorous analysis. Key numbers summarize the scope of the event. 2 worker fatalities, Hisashi Uchi and Masato Shinohara, making Tokai-mura Japan's first criticality accident with deaths in the civilian sector. 1 severely injured survivor, Yutaka Yokokawa. 667 people confirmed to have received measurable radiation doses above background. 161 residents evacuated from homes within 350 meters. Approximately 310,000 people advised to shelter indoors within 10 kilometers. 2.5 times 10 to the 18th fissions in a tank never licensed, designed, or intended to operate as a reactor. The IAEA's Lessons Learned report concluded with a statement that became widely quoted in nuclear safety literature. Design, operating procedures, and regulatory oversight must be regarded as an integrated system. Failure in any one can invalidate the others. The principle acknowledged that technical safeguards, administrative controls, and regulatory verification are not independent layers, but interdependent elements of a single safety architecture. Tokai-mura became a canonical case study demonstrating that safety margins cannot be evaluated in isolation. A facility with a strong design basis can fail if procedures drift. Rigorous procedures are ineffective if workers are not trained or if oversight does not verify compliance. Regulatory frameworks are hollow if inspections focus on paperwork rather than practice. In the record of civilian nuclear operations, Tokaimura stands as Japan's worst radiation accident before the Fukushima Daiichi disaster of 2011, not because of thermal megawatts lost, land contaminated, or populations permanently displaced, but because a handful of undocumented stainless steel buckets quietly defeated a carefully engineered safety geometry, turning a licensed chemical process into an unlicensed nuclear reactor that operated for 19 hours and claimed 2 lives.